Okay, so let's quickly go over an example of how we can apply DeMorgan's law. So right here I've got this equation, and I want to convert it. I want to convert it to an expression that's a lot more simplified, because when you look at this it looks kind of confusing. You have to think about it a lot before you realize what it says. So we can actually simplify this down so that it looks a lot cleaner. So let's look here. What should our first step be? Well, you realize that we can use these two things as an individual x and y. So now when you look at it, we have the equivalent of x and y inverted. And when x and y inverted, when you have x and y inverted, you can change that into an x naught plus a y naught. So we can change that to a or b inverted plus or a or c inverted. You have to keep that there because it's still there, inverted. So now we can do DeMorgan's law again, because now we have some more individual De Morgan laws here that are a little easier to see as well. So now we have A or B. We can change that to A and B individually, and then this can change into A and C, or A naught, and then since C is going to be double inverted, these two will cancel and it'll just become C, and those brackets stay there. And now we can simplify this equation even more. We have an A in both of these, or A naught in both of these equations. So let's pull this out to the front, and we've got A naught and B naught plus C, or C. And this is a lot easier to look at than what we had the original equation. So this is the very simple form of reason why we use De Morgan's law. It simplifies things a lot. Alright, so one of the applications of De Morgan's law in digital circuits, which is what we're learning in this class, is finding the equivalence between real gates and simple gates inside digital circuit diagrams, basically. So what are simple gates and real gates? Well, the simple gates here are the and or gates. These are the simple gates. And why do I say they're simple gates is because all we use them for is to basically find the logic in a full circuit. So when you have a circuit full of and or gates, it's actually really much easier to see any kind of logical error that you have and why you might be getting something. If there's something wrong with your circuit, you can see it much easier using these and or gates. When you have a circuit with NAND and NOR gates, it's actually much harder to see it, and you can see that down here in this example. This is a circuit that has NAND and NOR, a bunch of NAND gates, and you can see the logical equation that's associated with this circuit. It's got really crappy way of describing how this circuit works. So what we do is just convert it to an and or gate, or a simple circuit right here, and we have a much cleaner equation, like a much cleaner equation. And it's really nice to look at that, much more nice to look at that than it is to look at this. So a tool that we use to help us simplify these circuits is looking at equivalent gates. So basically this is just something you have to memorize. Let's just label this as the real gates. And I forgot to describe why it's a real gate. So they're real gates because these are the gates that we have to actually use when we're constructing a circuit. And I won't go into details about why. It's just we have to use these to construct. So When you have an AND gate, you want to convert it, and you want to find its equivalent gate inside the circuit. You have to switch it to an OR gate. If you can tell it's an OR gate, it just looks really bad. It's an OR gate, and it has two inverted input signals and an inverted output signal. And then when you have a OR gate here, its equivalent is an AND gate with two inverted input signals and an inverted output signal. It's kind of weird to look at the equivalent circuits of these AND and OR gates. Now you have your NAND and NOR gates, and they're just basically opposites of each other. So the NAND gate will be switched from its original form into an OR gate with two inverted input signals, and then a NOR gate will be switched to a NAND gate with an inverted output signal. That's how simple these equivalent gates are. So next we'll go into how we actually simplify or convert these circuits from real to simple, and then actually back from simple to real.